Squared.
All right. Hey, first of all, chi-squared looks like that. That's chi-squared, okay? It's chi. There's chi sound. All right. So, goodness of it, we're gonna look at a sample count, and we're going to be able to determine whether our sample count fits with what we think our actual count should be for any given scenario, or for some given scenario. So one such example would be this idea of this Gen A.
Gen A made a six-sided die from ceramics and rolled it 60 times to test if each side was equally likely to show up on top. Problem is, assuming that the die is fair, calculate the expected count for each possible outcome of Gen A's rolling.
Yeah? Forrest Gump. Huh? You feel like watching Forrest Gump?
It's the most beautiful.
Alright, so if the die is fair, what should our expected counts be for each outcome? So she rolled it 60 times, right? We're looking for an expected value, essentially. All right. So each outcome has a 1/6 probability of occurring, right? And then we do it 60 times, yeah? So if we were to roll this die 60 times, what we're saying is that we expect that each number should show up 10 times. So with our chi-square distribution, we can take a die, roll it 60 times, and look at our counts of each number. And based on those counts, determine if it is indeed a fair die. You know what I mean? That's what chi-squared is for. All right. It's chi-squared. I have a tendency to say it's chi-squared because for some reason you normally say squared and not square, but it's chi-squared. All right. All right, so let's calculate our chi-squared statistic. And I'm going to do this. So our chi-squared. And that sum, right, is all of our possible values for some sort of a categorical variable. Okay? This is the sum of all possible values. And that's where we use chi-squared the most, right? We want to know, hey, are there as many blue M&Ms as they said, right? So the outcome blue is a categorical variable, right? So we'll use chi-squared. And if you see a categorical variable, you're probably going to be thinking chi-squared. You're going to count a number of blue things, right? The outcome is not 4. The outcome is blue. You're going to use chi-squared. All right. Let's go ahead and calculate a statistic. All right. So Jenna rolled the die, and she got this real close. Right. There are a lot of people that want to do that for a living, I think. So here we go. We got Jenny's ceramic die and her expected counts. Obviously, the expected counts we calculated already. So let's go ahead and calculate our chi-squared value. Okay? So it's the sum of all of these, yeah? So outcome 1, it's always going to be, so it is observed minus expected squared over expected plus observed minus expected. And we'll just keep going through. Now guys, if you're doing this on your test, okay, on your AP exam, obviously you're going to put these things in your calculator, right? And just get a statistic. So it is actually sufficient for you to go all the way to the last one. And then put your final chi-square test statistic here. 3.4. Huh? 3.4? For all of it? Even in between stuff?
Yeah. So it's like 9 tenths plus 1 tenth plus 16 plus 14 plus 0 plus 14.
Yes. Sorry, I was looking at something different. I was like, right. You got it. All right, so we calculated a chi-squared test statistic. Yay! It's not bad. It's really not. All right. All right, so that was not what I wanted. Also, it's good to know that our counts are always going to take on positive values or non-negative values, right? This is always going to be skewed to the right. And we're going to find it by finding degrees of freedom. So let's go ahead and go through and actually look at these. All right. Let's calculate a p-value for Janie's die. All right. Okay, so let's look at our so we're using degrees of freedom. In this case, let's calculate our degrees of freedom. So our degrees of freedom, it depends on our number of counts. Or number of outcomes. So in this case with the die, our number of outcomes was 6, right? We had 6 possible outcomes. Huh? Yeah. So we will go to our table. So this is how we'll use it. We're going to look at our degrees of freedom. 5. Terrible example. So this is not a great example because our test statistic is actually so we would be looking for a value somewhere around what we're looking for is 3.4 on our table, right? And unfortunately, it's not here, right? So what that does, so this is our p-value. And unfortunately, this value, our p-value for 3.4 is actually going to be greater than 0.25. So, bad example. Let's actually get you one that's better, that shows you how to use the table better. In your book, I believe that they have a better p-value. So first of all, let's go ahead and finish this problem. Alright, so because of this, we're going to have a p-value greater than 0.25, right? Perhaps to do another example, take this stick there. What does that mean? If we have a p-value greater than 0.25, we put that into context, right? We're saying there's a pretty good chance that this outcome didn't just happen by chance, right? So we have evidence that this is a fair die. And it's weird because you would fail to reject our null hypothesis to find the null hypothesis. I'm going to have to find a better example. So let's actually do something different. Because that example is really bad. I'm trying to use this example that goes way back. So imagine if we got a chi-squared statistic of 1.180. Let's find our p-value. So let's find a p-value based on this. So weird. Let's just find p-value. Because I think that was a bad example to find a p-value. All right. And let's find our degrees of freedom. So what if we had degrees of freedom equal to 5? All right, so again, we're going to look here. But now we're looking for a value of 10.18. So that is going to be between 9.24 and 11.0 seconds. So then we can say that our p-value is somewhere between 0.1 and 0.05. And we're going to do these in the calculator and we'll actually get an exact p-value. So that's how you find it using the table. Sorry, it's a much better example than what the book came up with. All right.